I find that time and again when you look at the history of science that the null results where you expected there to be something are the most interesting. Like the whole of relativity is based on a null result, and then I mean when the LHC went online, everybody was kind of secretly hoping that we'd just look for the Higgs and it wouldn't be there, and everyone would freak out and have to come to something new, because you look for something that you expect to see and you see it.
Yeah.
Well, what do you do now? You're stuck, especially if you've got deeper theoretical problems that you don't understand. There's no clues into what to do next.
But it is still cool also to discover something and see something for the first time. One of my favorite activities with the MOST Space Telescope, the science we've done, is what I call ultrasound of stellar embryos. And so we're studying the vibrations of stars before they're even stars. They're still in the womb. And we're using sound waves, and so it literally is ultrasound. And we have been able to test the models that, as a student, I learned in courses at university, in the textbooks, of how a cloud of gas, a nebula, would collapse under its own weight and fragment and form a cluster of stars, and what would happen to that protostar, if you will. And technically, protostar really refers to only kind of one stage of what we call pre-main sequence evolution, but cut me some slack. Don't tell any of my colleagues that I'm using the more generic term protostar. Yeah, protostar just sounds cool. And pre-main sequence, we sometimes have to be very careful, because the main sequence is the term for when a star is in its sort of stable adult life, fusing hydrogen into helium in its core and not expanding or contracting. It's in an equilibrium. And the sun has been in that kind of equilibrium for about 4.5 billion years, and probably will remain so for another 5 billion years at least, maybe more. So we talk about main sequence, but before a star is a star, it's pre-main sequence, and that's abbreviated PMS. And so sometimes we have to be careful talking in other things in terms of there are other connotations to the term PMS, which brings me back to a time when I was a student at the University of Toronto studying astrophysics, and I was very fortunate to be involved in research. I was an author on 3 refereed scientific papers before I had gotten my Bachelor of Science degree. And I was telling a friend about one of these papers, one of these projects, in a cafeteria. I think it was the New College cafeteria at U of T. And I was describing how I was studying period changes in degenerate white dwarfs. And this woman stopped and came back and said, "Excuse me, I couldn't help but overhear your conversation. Are you, studying some kind of abnormal gynecology?" And I had to explain that the period referred to pulsation periods, vibration periods, which change due to the evolution of a star. And in an astronomical context, evolution is just how things change from birth to death. It's not a natural selection type process. And that white dwarfs are the corpses of stars like the sun when they die, and they're referred to as degenerate objects because they are not being held up by an ordinary gas pressure, the ideal gas law. They're being held up by a quantum degeneracy pressure, an electron degeneracy pressure, and so we refer to the gas as being degenerate and the objects as being in a degenerate state. So period changes of degenerate white dwarfs has a very clear meaning for astrophysicists, but it has a completely different meaning in other segments of our society.
And a coherent meaning as well for people who know nothing about. Like if you're talking about studying PMS in embryos, then at least there's the idea that, well, something's wrong there.
Well, the only complaint that someone, if they interpret it that way, of course, is we using the term dwarf, and we can talk about a dwarf star. The sun is a dwarf star in terms of being in the main sequence, and a white dwarf is just that terminology, and we have brown dwarfs as well. But the plural is not dwarfs, so it's not like Snow White and the 7 dwarves. it's some white star and the 7 dwarf stars. And so the plural in the astronomical context is not dwarves, it's dwarfs. So somebody might have caught me out if they thought that I was really doing something different than astronomy, that you should be saying dwarves, not dwarfs.
If they were paying attention to exactly the phonemes that were coming through.
Well, exactly. And I suspect that the other words were probably a little more distracting, and so they probably weren't going to correct my grammar or my spelling on the use of that. But that, going back to the original topic, we were actually able to kind of follow the birth, the gestation of a star before it became a star. Now, even that process for stars, like the sun, that's a process that can take, many millions of years, and astronomers don't last for millions of years. But fortunately, we live in a city of stars, and I'm not stealing that from La La Land. I actually would refer to that even before La La Land came out. I think of our Milky Way galaxy as a city of stars. Metro Milky Way. We live in the suburbs, out near the edges, where the Surrey of Metro Vancouver, or where the Etobicoke of Metro Toronto.
Where you're less likely to get passers-by giving you trouble and ripping you to
That's right.
shreds.
But so we have this, and it has a population of hundreds of billions of stars. In one of your musical numbers, you refer to a subset of those of something like 40 billion stars. But we live in a very populous city of stars, and just like any city of human beings, you have citizens of a wide range of ages, from babies to senior citizens, of different backgrounds and so on. And so we can take a census of part of the population of our Metro Milky Way, and so we can actually see examples of different stages in life and even pre-life, if you will, there. And so that's how we're able to put together, the life story of a star like the sun, which would be 10 billion years from birth to death, or following the gestation of a star like the sun before it's even born, which could take millions of years, because we can look at different examples at different stages. And I just find that, that very cool. And we haven't even started to talk about exoplanets.
So it's like you've got a single snapshot of a crowd, and from that you construct sort of like the archetypal life of a human being.
Absolutely. Think about it. If there are aliens out there, and I think there are, and they were like an alien anthropologist or an alien anthropology student sent on a field trip, and one of the stops was Earth, but they only had like an hour to be on Earth, and the instructor was trying to make the students be, fairly resourceful. And so saying, you can't use any information resources. You can't go on the web. You can't go to a library. You just have to make non-invasive, passive observations of human beings. And in an hour, I want you to construct the entire life cycle of a human being. And, if those alien students were smart, and if they're capable of traveling across interstellar space, they must be reasonably smart. What they would do, I think, is to go to a place where lots of humans gather. A street corner in a shopping district of a big city, Robson and Burrard, here in Vancouver, or Yonge and Dundas in Toronto, or anywhere on, Rue Sainte-Catherine in Montreal. And just for an hour, just watch who goes by. And you are going to see a cross-section of the entire life cycle of human beings. You're going to see babies pushed past in strollers. You're going to be seeing senior citizens maybe going past in walkers or wheelchairs. You're going to see kids running by. You're going to see adults, going to work, shopping. You're going to see an entire sample of the life cycle of a single human being, from just after birth to just before death. And if you pick the right street corner, you might even see examples of those two things. And so in a short period of time, with a large enough representative sample, you could actually put together a pretty good picture of how human beings change from birth through their lives to death. And that's what we do with with stars, except now we don't just have a sample of, a few hundred or a few thousand people going by a street corner in an hour. We have, at least to draw upon, a sample of several 100 billion stars in our own galaxy. And then we've got the other cities, other galaxies there where we can kind of look at the big picture, compare the demographics from one city to another. So, we can, compare Vancouver to Istanbul, to Cape Town, and look at the differences in those populations.
Are there compositional differences from one galaxy to another?
Yes, there are, actually. So the big picture, the recipe for stars and for the normal matter in the universe is pretty simple. It's basically three numbers. Astronomers like to break things down by mass, by weight, not by number of atoms or molecules. And so the first number is X. That's the fraction of the normal matter in the universe that's hydrogen by mass. And then the next is Y, that's the fraction by mass of helium. And those two numbers together add up to about 98%. And everything else that's in the periodic table is about 2%, 1 or 2% by mass. And so we lump it all together in one number we call Z. And so that's all you need. The recipe for normal matter in the universe is basically three ingredients. Now, the third ingredient is a mix of lots of different things, but there's not very much of any of those things. And we used to think that normal matter was the entire composition of the universe. The stars, the gas between the stars, the planets was all made of this matter, and then there was energy, and that was it. But before I had graduated from the University of Toronto, a woman, Vera Rubin, who passed away recently, as a graduate student and then as a young astronomer, had finally shown us that what you see isn't always what you get. Is that when you try to sum up the masses of galaxies, including our own Milky Way galaxy, in terms of the stars and gas you can see, that you fall short, that there was missing matter, as it was called at the time, and we now refer to it as dark matter. And that could have represented up to like 10 times the amount of mass of what we used to think made up the universe. And then, about 14 years ago now, there was compelling evidence through supernova observations in distant galaxies that the expansion of the universe wasn't slowing down under gravity, it was actually accelerating due to something which we call dark energy, which is just a placeholder name because there was already dark matter. Could have called it George, Hermione. Eric Idle had a great name for it. He wanted to call it levity, that gravity was the contracting force of the universe and levity was the expanding force of the universe. And Eric and I had a kind of a debate conversation on Space, the Imagination Station once. I just wish he'd come along with it earlier because maybe it would have caught on, but now we call it dark energy. 75% of the mass energy budget of the universe is dark energy. We don't know what it is. About 21% of the mass energy budget of the universe is dark matter. We have culprits, and I would be confident within maybe another 5 years or so, we probably will have figured out what are the major contributors to dark matter, but it's fair to say right now that we don't really know what that is. And so that means something like 96% of the universe, the recipe for the universe, is stuff that we don't know. And what we used to think, when I was a student, it was 100% of the universe is relegated to 4% by mass. And that might be kind of depressing to people. We used to be, in the recipe of the universe, we used to be the main ingredient. And now we're not. Now we're a condiment. But now, to be honest, what I think of it is as a spice. Because of that 4% by mass, roughly, much of that is not the stuff that makes us up or makes up our planet Earth. And so if you worked it out, what makes us up is probably something like, 0.1% by mass. Don't quote me on that. I haven't done my homework, but it's a very small fraction.
I'll fact check you and put you in the bottom.
Well, these are alternative facts. Bring in Kellyanne Conway, and she'll back me up on this, I'm sure.
I'm having her on next week.
All right. But we're the spice. We're the flavor of the universe. And think of it. Would you want to go to a restaurant that didn't have any spices or flavor in the food? Would you want to live in a universe that had no flavor? I mean, I think these ingredients, and we're the known example of those ingredients coming together in a form of life, and I believe that there are other places where that will have happened. But even if it were just us, we're what makes the universe interesting, because we can kind of appreciate the universe. We can study it. We can be aware of it. If you can imagine being in a universe in which there was no life or no sentient life, it goes back to those kinds of discussions you'd have at odd hours over beers with your fellow philosophy students in university or college. If a tree falls in a forest and there's nobody to hear, does it make any sound? If there's a universe which has, stars and galaxies, but there's no sentient life, does anybody care? Is that an interesting universe? There's nobody in it to appreciate it. So I think the fact that we are the spice of our universe, and a spice which is self-aware to understand at least certain aspects of a universe which is so vast, even though we occupy such a tiny part of it, I think that's the coolest thing ever, and I don't think that should depress us or make us feel insignificant. It should make us, feel really great about ourselves. Not too full of ourselves, but at least the fact that we're pretty lucky. In some sense, I'm living my dream as an astrophysicist, but we're all, in some sense, living a dream because we live in a universe that we can admire and appreciate and understand and wonder about. And you don't have to be a rocket scientist to wonder, where did it all come from? What's going to happen in the future? Is there life elsewhere? Do we have neighbors? How did the sun and planet Earth form? How did life come to be here? Those are the kinds of questions that, many people have asked and continue to ask, and they don't have like letters behind their names. And they, my parents, who were not highly educated, would ask those questions, and they usually went to me after a while for answers. And so I think we're all, as a species, we are fulfilling a dream, and many other species that aren't intelligent or self-aware, they don't even know that they're missing out on that dream because they're just not capable of dreaming. So even though we're a tiny fraction of the universe in spatial scales and mass and almost every criterion that you can think of, we matter because we're observing it. We're the audience. The universe is an amazing performance, but who cares about a performance if there's nobody else to see it? Even if you're performing alone, I can dance in front of a mirror, or if I can sing in the shower and I hear myself, so I'm the performer and the audience. But imagine a universe where there's a performance and there is no audience. And we're not in that universe. And if we were, of course, we wouldn't be having this conversation. I'll shut up now because I'm kind of rambling at this point.